From our last lesson, we realized that every atom and molecule either is or can be a dipole. Since most objects are made of a bunch of atoms or molecules, most objects are made of a bunch of dipoles. So for this lesson, we are going to try to figure out the electric field and electric potential from these collections of dipoles. So first, we are going to introduce a new term called the dipole moment per unit volume, represented by a capital vector P. Now, if this is uniform, the dipole moment per unit volume is equal to the sum of all dipole moments divided by the total volume. However, dipole moment per unit volume might not be uniform, and the equations we use might depend on position. So a more precise definition of dipole moment per unit volume is the sum of all dipole moments is equal to the integral of dipole moment per unit volume with respect to volume. Also, as a brief reminder of what our various r's mean, you have vector r, which represents our position. By our position, I mean the position that we are interested in. R prime vector represents the position of the charge or other object that is creating an electric field or electric potential at our position. And script r vector is equal to r vector minus r prime vector. It's the vector that represents how far away our point is from the point that has the charge. So with this, I am going to be referring to equations in the textbook. I am going to be starting on page 173. To start, the potential of a single dipole is given by equation 4.8. Again, lowercase p is the dipole moment of that single object. Script r hat is the unit vector of script r. Next, to find the total potential contributions of all of those dipole moments, we add them together. But again, adding a bunch of dipole moments is equivalent to integrating this dipole moment per unit volume with respect to volume. And so that's how we get equation 4.9. Next, the textbook does something a little clever. It notices that the value of r hat divided by r squared is equal to the gradient of 1 over r. Specifically, the text uses the gradient in the prime coordinate. This lets us write our potential equation in the form that you see at the top of page 174. Next, the textbook uses product rule number 5 to rewrite this. So, reminder, product rule number 5 is this product rule right here. The divergence of a scalar function times a vector function is equal to the scalar function times the divergence of the vector function plus the vector function dotted with the gradient of the scalar function. So as you can see from the top, or from that equation at the top of page 174, p dot del of 1 over r, that's this right here. P is our vector function, and 1 over r is our scalar function. So we could write that term, p dot del times 1 over del of 1 over r, as equivalent to this term right here, which is the first term in the equation right below it, minus this, which is the second term in that equation right below. Lastly, the textbook uses the divergence theorem, which basically says that the integral of the divergence of a function, there's the integral of this over a volume, is equal to the integral of that function, or integral of just this, over the closed surface. And that brings to equation 4.10. So there are two terms in equation 4.10, two additive terms. One involves an integral of 1 over r times p dot dA, and the other involves an integral of 1 over r times the divergence of p. Well, 1 over 4 pi epsilon naught times the integral of 1 over r times something, that something is a charge, because remember, potential of a point charge is 1 over r. So that's why the textbook says that the first term, that p dot dA, looks like a surface charge, and the second term, negative divergence of p, looks like a volume charge. It is customary to refer to these as bound charges. For 4.11, that's the bound surface charge, and for 4.12, that's the bound volume charge. These are called bound charges as opposed to free charges. Free charges are, for example, in a metal, when an electron is allowed to move however it wants, as long as it stays within the metal. That is a free charge. The charge created from dipoles, the individual charges are not allowed to leave the molecules or atoms that they are a part of. That is why they are bound. But these charges are real. So continue to page 176. Look at the diagram in figure 4.11. You can see that if you do in fact have a bunch of dipoles, and remember, a dipole is just two charges of opposite sign that are really close to each other. If you have a line of dipoles that are all lined up in the same direction, a bunch of those charges will end up canceling out, and the net result is a single dipole with one charge, with a negative charge at one end and a positive charge at the other end. So even though the figure on the right of figure 4.11 looks like it's just two charges, those are analogous to the bound charge or the bound surface charge of equation 4.11. In figures 4.12 and 4.13, we can see that the amount of bound charge does depend on the surface itself. So again, consider in figure 4.11, because that is a dipole, the charge on the left and the charge on the right must have equal magnitudes. In figure 4.13, if we imagine there are a bunch of those long dipoles in there, then the total charge on the left surface must equal the total charge on the right surface. But because of the way that the cylinder is cut, the right surface has a larger area, which means the left surface will have a lower charge density, since that same amount of charge is spread over a larger area. In figure 4.14, we can see what happens if the polarization is changing either magnitude or direction. We end up with some charge bunching. In the example shown, the polarization is pointed outwards from a point. And so you have a bunch of negative charge bunched towards the inside, and a bunch of positive charge spread out over the outside. If, for example, this were a sphere, with the polarization always pointed radially outward, this would mean there would be a negative charge on the inside of the sphere, the bound volume charge, and a positive charge spread out over the surface of the sphere, the bound surface charge.